So in this video, we are going to start looking at different types of reactions. You do want to make sure that you feel relatively confident with the naming and drawing, because once you get into types of reactions, we're generally going to give you a name, and you're going to have to be able to draw something out to be able to go from there. So first type of reaction we talk about for organic molecules are combustion reactions. We've been talking about combustion reactions since grade 10, so this shouldn't really be anything crazy new. So combustions of hydrocarbons are considered to be an organic reaction, and that's because hydrocarbons contain carbon and hydrogen, therefore they are organic molecules. So when we are looking at a combustion reaction, you're going to be able to recognize that something is a combustion reaction because you're going to find you're always going to have whatever your hydrocarbon is, and then it's going to be plus oxygen. Okay, another thing you're sometimes going to find, and they sometimes do this and sometimes they don't. Sometimes what they do is they'll put an arrow in, and then over the arrow they'll write the word spark. They don't always do that, but they definitely do that sometimes. So biggest thing you are looking for to recognize that something is going to be a combustion reaction is this plus oxygen. Okay, you're going to find that as we go through the different types of reactions, similar to when you learn types of reactions in grade 10, we're always going to kind of have something that we're looking for in our reactants that's going to tell us that it's a certain type of reaction. And whenever we see that something is plus O2, we're going to recognize that that means it's combustion. And so by default, as soon as we know something is combustion, we know that we have to be making carbon dioxide, I'm not hitting the right buttons, plus water, right? And that water should be a vapor. Okay. And yeah, you just have to make sure that you balance it based off of whatever coefficients you need based off of your hydrocarbon. Okay, so your second type of reaction is an addition reaction. So now we're getting into things that are entirely new. So addition reaction occur for alkenes and alkynes, right? So remembering when we talked about alkenes and alkynes, our alkenes had double bonds and our alkynes had triple bonds. Okay, remember we talked about molecules as being saturated or unsaturated? What you're going to find is addition reactions are reactions that occur with those unsaturated molecules. And basically they turn something that's unsaturated into something that is saturated. So really for the most part, when we're trying to identify an addition reaction, we're looking for there to be a double or a triple bond between our carbon atoms. If we don't have that, then it can't be addition. If we do have that, then chances are it's going to be addition, okay? So what happens in an addition reaction is we add a small molecule, okay? That small molecule could either be water, could be hydrogen, could be an HX, or it could be an X2, okay, where X is basically any of those halogens that we have talked about. So depending on what your small molecule is, that's going to determine the type of compound that you can actually go about making. So if we look at this slide, this is kind of a general kind of breakdown of what this looks like, right? So here we have an alkene. We can tell that because we have a double bond. And here are kind of those four options, right? Option 1 is we add hydrogen. Option 2 is we add water. 3, we add HX, again, where X is any of those halogens. And 4, where we add X2, okay? So depending on which small molecule I add, that's going to determine the type of final product that I make. So in general, what happens in an addition reaction is the double bond goes away. So we went from something that had a double bond to something that's a single bond, right? So if you think about that, we now have a carbon with a single bond to another carbon. But it still has those same two things attached that it had before, right? When you look over here, it had two things. But now what's happened is the double bond's gone away and it's turned into a single bond. So what that means is we now have some openings, right? We have an opening here and we have another opening here. And that's because, like we've talked about before, every carbon wants a total of 4 bonds. And by getting rid of that double bond and turning it into a single, each carbon right now only has 3. So when you look at your small molecules, they're kind of written over here as having two parts. And the reason they're written as having two parts is because one part is going to go into this slot, right? So if I'm looking at this one, this hydrogen is going to come over here and go here. Some lovely arrows that I'm drawing. And this hydrogen is going to go here and fill in the other spot, right? And so that's how we're going to be able to make that alkane. When you look at the next option, we added water. So they've written water as HOH. And that's because the H goes into one slot and the OH goes into the other, right? They each went into two different slots. So one thing we find with these alcohols is that there's the possibility for two isomers. Okay, the reason there's the possibility for two isomers, so remember isomers means they have the same molecular formula, but they have a different drawing and a different name, is because how this OH and this H go in, they could have gone in the other way. If I have a really small molecule, it's not going to matter, right? Because think about naming, we prioritize that alcohol group. But if I have a larger molecule, I may find that I have two different possibilities. One where, let's say the alcohol went on, I don't know, carbon number 2, and the other one where it went on number 3. And I would want to make sure that I'm showing both of those options. Okay, the next small molecule is HX, so same idea, there's two parts to it. The H is going to go onto one of the carbons, the X is going to go onto the other. This one is similar to alcohols, and that also has the possibility for two isomers. Okay, the reason it has the possibility for two isomers is when we look at the two parts, they're not identical, right? You'll find that that's true for when we add water and when we add HX. When we split this into two parts, they're not identical pieces, which is why we have the possibility for those two isomers. Okay, we look at our last option, which is plus that X2. And we find here we go back to just having one possibility. And that's because both of these parts are identical. So it doesn't matter which one gets what, it's still going to be the exact same thing, okay? So if we add hydrogen, we turn an alkene into an alkane. We add water, we turn an alkene into an alcohol with the possibility for isomers. We add HX, we turn it into an alkyl halide, which again has the possibility for isomers, or we add X2 and we turn it into an alkyl halide. Okay, so looking at some examples, okay? So this is where I'm saying being able to draw from a name becomes really important. So we are doing butene plus chlorine. So first thing we want to do is we want to go about actually drawing out what this molecule is. So when we want to draw butene, we want to recognize that but means 4 carbons. So 1, 2, 3, and 4. Okay, you're generally going to find that when you get into doing these types of reactions, it tends to be most helpful to draw the full-on structural diagrams, and that's just that you can really see where things are. Doesn't mean you can't do a line diagram or you can't do a condensed. It just sometimes makes it a little more obvious what you're doing. Okay, so there's our but. It's a 2-ene, so that's telling us we need a double bond here. And then everything else gets to get filled in as a single bond, right? Then we got to fill in those H's, right? There's got to be H's there. There's got to be 1 here, 1 here, and 3 here. Okay. So then, finish drawing all of that in. It's going to be a faster way to do this. Hold on. Didn't go where I want it, but let's see if this goes better. Okay, so we want to fill those pieces in so that we know what we have where. Now we are going to be adding chlorine. Okay, so we're adding that Cl2. So we can write it as a Cl to Cl. Okay, so I'm going to recognize that this is addition. The way I'm going to recognize that this is addition is I have that double bond and I'm adding something that is small to it. So once I recognize that that's what it is, I need to know that addition means I'm going to get rid of the double bond. I'm going to turn it into a single. So that's going to be the next piece that I do. So let's go ahead and draw that out, right? So we're going to have a carbon to a carbon to a carbon to a carbon. Just a few spaces in there to spread this molecule out a bit. Okay, we've turned that double bond now into a single bond, right? We fill in all those H's that were there before because we're not getting rid of anything, we're adding something, which is why it's called addition. So try to move things, line them up a little better. So now what we're going to have to do though is we're going to have to add those chlorines in. So we still have all of these that were here from before. Now what we're going to do is we have these two carbons here, which are right now when we look, they only have 1, 2, 3 bonds. So we need to fix that. We're going to fix that by giving each one of them half of that small molecule. So if we look at our small molecule, it was a Cl and a Cl. So that means one of these is going to get a chlorine. And then because both parts were chlorines, the other one is also going to get a chlorine. Okay, so we did an addition reaction. We turned an alkene into an alkyl halide. So naming wise, it's still going to be a bute, but now it's going to be an ane. It's going to be butane because everything is a single bond. In our prefix, we need to indicate that we have these two chlorines. So because there's two of them, we're going to call it a dichlora. We need some numbers to show where they are. They're at carbon number 2 and carbon number 3. So it's going to be a 2,3 dichlorobutane. Okay, so when you do addition reactions to alkynes, these can be a little bit different. And the reason they can be a little bit different is they have triple bonds. So the question becomes, when you're doing addition to an alkyne, are you turning it into a double bond or are you going all the way to a single bond? The way you're going to figure out which one you're doing is you're going to look at how many of that small molecule it gave you. So here you'll notice the word excess is used. And excess means I have as much of it as I want. So whenever I see the word excess, that means that I'm going to be able to take that alkyne all the way down to an alkane. If it said that I had a limited amount, then I'm only going to be able to take the triple bond to a double. So I'm just going to turn that alkyne into an alkene. Okay, so we have ethyne. So eth, 2 carbons. Ine means we have a triple bond. Okay, we need to make sure that we give every carbon 4 bonds. So that means each one of them is going to get a hydrogen. Okay, we're now adding excess chlorine. So we're going to add those chlorines. So what you're going to find though is because we have excess, we can use as many as we want. And we're actually going to use 2 of them. Okay, the reason we're going to use 2 is we need one to take the triple bond down to a double bond, and then we need a second one to take the double bond down to the single bond. So anytime you have a triple, you know that you're going from an alkyne to an alkane. Either it says excess or it shows you that you have access to 2 of them. You would only take the alkyne to an alkene if it said limited or it showed you that you only had 1 of them. Okay, so I'm going to recognize that it's addition because I have that triple bond, right? I have a triple or a double bond, almost automatically always going to mean that. So now what we're going to do is we're going to take that triple bond and we're going to turn it into a single bond. So then when we look at this, each one of our carbons now only has 2 bonds. We know that we need to get it up to 4. So we're going to have to attach 2 things to each one of these. When we look at it, we added 2 of these chlorines, which means in total we have 4 chlorines, which is good because I have 4 empty spots. So one of the empty spots is going to take 1 chlorine. Another one's going to go over here. And then the same thing is going to happen down here. We're going to add those chlorines in. So we turn it into this. Okay, so naming wise, it's still an eth because there's 2 carbons, but it's now an ane, right? It's ethane because everything is a single bond. We now have 4 chlorines. So we're going to call it a tetrachloro to indicate that we have 4 of them. We do still need some numbers because we need to show that there's 2 on this one and 2 on this one, right? There are other options. I could have had 3 over here and 1 over here, but obviously that didn't work because we already had a hydrogen attached to each one of those. So naming wise, it's going to be 1, 1, 2, 2, dash tetra chloro ethane. Okay, so this is the same example. The only difference now is we have switched over to a limited amount of chlorine. So our starting molecule is still the same. It's still going to be ethyne. So we still have 2 carbons. We now have a triple bond between them. I'll fix that into a triple in just a second. There we go. Looks a little different, but that's okay. And now we have a limited amount of chlorine. So that means we only get to add in a single chlorine. Okay, so recognize its addition because I have that triple bond. But because it's a limited amount, we're only going to be able to take that triple bond down into a double bond. So we turn it into this, which now when we look at it, we can see this carbon has 1, 2, 3 bonds. So we know that it's short one, right? It needs 1 more. The same deal over here. This is short one because it has 3. So now it gets to 4. I have a chlorine and I have a chlorine. So on this guy, we're going to put chlorine. And then we're going to do the same thing over here. We're going to put that second chlorine. So last example, we were able to turn it into an ethane because everything was a single bond. This isn't an ethane. This is an ethene because we do have that double bond. Okay, we do have 2 chlorines, so it's going to be a dichloro. So it's going to be a 1, 2 dash dichloro eth, and then ene. Okay, we don't need to indicate that it's an eth1ene because there's only 2 carbons, so there's really only the 1 spot for that double bond to go. Okay, there are no other options. Okay, so now we get into a little bit larger of an example, right? Now we have pent2ene plus hydrogen monochloride. So we think about pent2ene. We have 5 carbons, so 1, 2, 3, 4, 5. Right? We know we have some single bonds, but we also know that we have a double bond, right? And we have a double bond after carbon number 2 because it's a 2ene. Okay, so let's fill those other bonds in. Now when we look at it, we know we need to fill some hydrogens in, right? So this has 1 bond. It needs 1, 2, 3 things more. This has 1, 2, 3. So we need 1 more hydrogen. Same thing here. This has 1, 2 bonds. So it needs 2. This only has 1. So it is going to need 3 of those hydrogens, okay? So now we can pop those H's in. Don't know what I did there. Okay, that's where I wanted that to go. Okay, let's just try that again. And then these slots here. Okay, so now we are adding hydrogen monochloride. So that means we're adding a small molecule that is not the same throughout, right? It has 2 parts to it. It has, oh, my caps lock's on. It has an H and it has a chlorine. So again, I'm going to recognize this is addition because I have that double bond. That's kind of the only option that we have, okay? So we are going to turn this into a single bond. So we're still going to have our 5 carbons. Okay, now everything has has single bonds between it. We're filling in all those other hydrogens that we know we already had before. We get there slowly. Okay, so once we get all our H's in, then what we are going to do is we're going to take care of this HCl, right? So same as before, we look, and now when we see this carbon here, it's only 3 bonds, and same with this one, right? So this is where drawing that structural can be a little helpful because it makes it kind of obvious where something needs to go, right? I have this big gap here, so I know that something has to go here. So this is where I have the possibility for isomers, right? I'm adding a molecule that is not symmetrical. So option 1 is that the H goes here and the Cl goes over here, right? But the other option would have been to switch that H and that Cl around. Okay, so had we switched them around, right, we would have started with that same thing. We would have gotten rid of the double bond, turned it into a single. We would have recognized that these 2 carbons were each short a bond. But now when we place them, instead of putting the H on the first one and the chlorine on the second one, we would have put the chlorine here and then the H over here. Okay, so we have the possibility here for 2 isomers. And the reason we get 2 isomers is because the small molecule was not symmetrical. Okay, so naming wise, we should still be able to name both of these. So when I look at this one, right, it's now a pentane, and the chlorine is attached to number 3, so it's going to be a 3-chloropentane. When I go to name this one, the chlorine is now on number 2. So this is a 2-chloropentane. Okay, so possibility for 2 isomers because 1, it was a bigger molecule, and 2, we were adding something that was not symmetrical. Okay, last example, we have propene and HCl. So we think about prop, it has 3 carbons, right? It's an ene, so one of them is a double bond. The reason there's no number given is it really doesn't matter which one we turn into a double and which one we put as the single, okay? So same thing, we're still filling things in. This carbon has 2, so it gets to get 2 more things. This has 1, 2, 3, so it gets 1 more. This one has 1, so 2, 3, and 4, right? Where obviously those blank spots all have hydrogens in them because we always assume that there are hydrogens. Because if it wasn't a hydrogen, there would have to be something in the name to tell us that it was not a hydrogen. Okay, so this time around, the molecule we are adding is an HCl. So again, similar to the last one, we have 2 options, right? The H and the Cl can each go into different parts. So we're going to find we have our first isomer, and then we have our potential second isomer. Right? They both start by having the same thing happen. They both start by having that double bond turn into a single bond. Okay, they each still have those same number of hydrogens that they had before. All right, pause the video and drew those out so you didn't have to go through the painful experience of watching me attempt to draw these on my computer. Okay, so basically what I've done is I've kind of set up the 2 possible options where I've gotten rid of that double bond, right? So if we look at the one over here, we now see how this carbon has 1, 2, 3 things attached to it, right? It's missing something here. And the next carbon also has 3 things. It is missing something here. So because we have HCl, right, one slot gets to get an H and the other one gets to get a chlorine. Okay, so first option, I'm going to put the H on the end. and I'm going to put the chlorine on that second one. Right? The other option, which we can draw over on the other one, is to just switch where that H and that Cl are. So we can put the Cl on the first one and the H on the other one. Okay, again, we wind up with two possible names, right? So the name for the one over here, because chlorine is on carbon number 2, is going to be a 2-chloropropane, right? And prop because of 3, ene because everything is a single bond. This one over here, the chlorine went on number 1, so it's going to be a 1-chloropropane. Okay, so two different options. Okay, so types of reactions we talked about today were combustion. You got to recognize combustion because it's plus oxygen. We turn it into carbon dioxide and water. Okay, you're going to recognize addition because your starting molecule has either a double or triple bond. Okay, that is unique to an addition reaction. Just like adding oxygen is unique to a combustion reaction. Okay, I didn't do examples of combustion because you've been doing combustion reactions since grade 10. So you should hopefully be okay with drawing those. You definitely will find, though, that as you go through your booklet, there are some combustion questions in there for you to practice. So really the only difference for combustion, the thing that's going to change from one question to the next, is just how many CO2s you make and how many H2Os you make. That's really going to be the only difference. Obviously addition, we are going to be making different products every single time. But yeah, so those are your first two types of reactions.